Hey guys, it's Mr. Patron, and today we're going to be talking about bond polarity. So, as of now, we've been focusing on two main types of bonds, ionic and covalent. We should recall that an ionic bond involves the transfer of electrons from metal cation to a nonmetal anion, whereas covalent bonding involves the sharing of these electrons between two nonmetals. However, within covalent bonding, we can also classify this in another fashion, and that's based on polarity. So when we think of the term polarity, I want us to think about the north and south pole of a magnet. So one side of a magnet has a positive end, while the other side of the magnet has a negative end. Covalent bonding uses a similar concept, as one side of the bond can have a stronger charge than another. We can observe this by using an example such as HCl. Hydrogen is a nonmetal, chlorine is also a nonmetal, so this is a covalent bond. But first, let's sketch out the Lewis dot diagram of HCl. So we know hydrogen has one valence electron. We'll put it right here for bonding purposes. And then chlorine has 7, and I'll do those in a green color, make them a little bigger. So we have 1 here, 2, 3, 4, 5, 6, and 7. And as we can see, now we have an octet for the chlorine, and then hydrogen also has its full shell with the 2 electrons there. Okay. And we can clearly see from this Lewis dot diagram that the chlorine has a much stronger negative charge, as it has 7 valence electrons surrounding it, while hydrogen only has 1. The fact that this chlorine side has a large difference in charge allows us to say that this covalent bond is polar. So bond polarity does have some important implications based on physical properties such as melting point, boiling point, solubility, as well as some other chemical properties such as how it reacts. But we'll get into that later. We can show this extra negative charge on the chlorine side of this compound by using an arrow, which will just point this way, as it shows us that the more negative charge is facing the chlorine as opposed to the hydrogen. You'll see this sometimes. It'll be more often taught in more advanced courses, but it's good to get this kind of exposure now. So just to quickly recap, the bond between hydrogen and chlorine, it is a polar covalent bond because chlorine has more of a negative charge compared to the hydrogen. So the negative charge is being pushed towards chlorine side. And a simple way to determine if a bond is going to be polar or nonpolar is through using its electronegativity. So as you should recall, electronegativity is an element's ability to attract an electron. And this increases as you go up and across the periodic table. So from the bottom left to the top right, fluorine is the most electronegative element with a value of 4.0. And we can find this on our table S in our reference tables. And so there's a general rule of thumb that we use to determine whether a covalent bond is going to be polar or nonpolar. And for that we use the difference in electronegativity. So the delta E, delta meaning difference. And in general, if delta E is greater than or equal to 0.2, we have a polar bond. If it is less than 0.2, it is nonpolar. And that is really all you need to focus on. Now just recall that this is for only covalent bonds. So an ionic bond between a metal and a nonmetal, you don't have to worry about these electronegativity values. You won't be asked to determine if it's a polar or nonpolar bond. For the most part, the electronegativity values of ionic compounds, their differences are much greater. So they inherently have a strong polarity, because one is already clearly positive and one is clearly negative. Here we have our two nonmetals, so we can't really determine right off the bat which one is going to be more negative or more positive. Okay, so we're going to go through a couple examples of this. So here I have HBr, hydrogen bromide. So to determine if this is going to be a polar or nonpolar bond, we have to find our differences in electronegativity. So first we need to find the electronegativity of hydrogen. So if you go to your table S in your reference tables, hydrogen is atomic number 1, and its electronegativity is 2.2. If you go to bromine, which is atomic number 35, its electronegativity is 3.0. So to find the difference, you're simply subtracting the two. So your difference in electronegativity is 0.8. Now here you're always going to find essentially the absolute value of the difference. So you're subtracting the smaller value, from the larger value. So you'll always end up with a positive delta E. So based on our rule, we know that if electronegativity is greater than or equal to 0.2, we have a polar bond. Our delta E is 0.8. So we must have a polar covalent bond. Alright, so let's try another one. We have a bond between carbon and hydrogen. So we need to find the electronegativity of carbon, hydrogen, and the differences. So hydrogen, we might recall from just doing the previous one, its electronegativity was 2.2. For carbon, which we know is atomic number 6, its electronegativity is 2.6. So therefore our difference, if we just subtract the two, is going to be 0.4. According to our rule, delta E is greater than or equal to 0.2, so we have a polar bond. Okay, and we'll just try one more. So we have a bond between carbon and iodine. So electronegativity of carbon, so let's go back to our table S, is 2.6. Electronegativity of iodine, which is atomic number 53, is 2.7. If we find the difference, 2.7 minus 2.6 is 0.1. Based on our rule of thumb, this is less than 0.2, so we have a non-polar